What? Did it just break the gauge?
I designed a compressor and asked you for improvements, and then this happened.
Look at all the comments.
After going through all the comments, I decided on the new concept. Let's remember what were the setbacks of the old design and how are we gonna improve on them. Primary problem is the vibration, and there are two components to that. First one is caused by the inertia of the pistons. They are moving fast and changing directions all the time. The second type of vibration is caused by constantly changing torque requirements of the piston. I will call these ones kickbacks to differentiate the two. To overcome the vibrations caused by the inertia, I changed the cranks. I added some slots to put some nuts in as counterweights. This counterweight is moving in the opposite direction of the piston. Therefore, hopefully it will cancel out some of the vibration. Let's talk about the second type then, the kickback. They are more important in our case since the compressor isn't spinning that fast. When the piston is compressing the air, it's both fighting friction forces and pressure forces. But in the intake stroke, it's only fighting friction forces. So when we plot out the torque requirement of the piston over time or over crank angle, we get a waveform. And when I'm spinning the compressor with a drill, I'm finding this constant change. So the first thing to do is adding a motor on board, so the chassis itself will fight these forces. And the second thing is smoothing out this graph so there isn't much change. The obvious thing to do that comes into everybody's minds first is adding another piston in the opposite direction. But then again, we have two options. The pistons can move opposite to each other or they can move together. If they are moving in the opposite directions, then the vibrations from the inertia cancels out. But the kickbacks basically doubles because their strokes are matching. Their torque curves are overlapping, and as I mentioned before, kickbacks are more important to solve in our case. Let's look at the other case then, pistons moving together. In this case, the vibrations from inertia basically doubles. But the kickbacks are much smoother because there is now a phase difference between the graphs. So when the piston 1 is compressing and it's requiring a lot of torque, the piston 2 is basically intaking and it's just fighting friction forces. So it doesn't need much. And then they change, and then change again. Another way of smoothing out the torque curve is adding a flywheel. A flywheel can store kinetic energy and release it when it's needed. So when the torque curve is peaking, the flywheel can help out the motors, and then when it's low, it can store energy from the motors. I also gave the flywheel another function by turning it into a gear. Now the motors can spin it to power the compressor. And hopefully it's big enough that it creates sufficient gear reduction for the motors. Last thing to discuss is adding a stage. Many industrial compressors have two pistons and use the second one as a second stage. How it works is, first stage compresses the air and then pushes this already compressed air into the second stage, and the second stage is compressing it again. But there's an elephant in the room that we have to discuss, which is heat. When you compress air, it gets hot, and if you compress it again, it gets even hotter. My PLA cylinder heads will simply melt. It's not a good idea to put already hot compressed air into a second PLA cylinder head and then compressing it again. To solve this problem, the first ever sponsor of my channel comes in handy, GLC CNC. They offer an incredible service where they produce your design and then send it to you within a couple days with really competitive pricing. I used their PCB services before they even sponsored me, and I can confidently say for makers like me and small businesses, they offer a great service, allowing us to create stuff that wouldn't be feasible just a few years ago.
And it's really simple to order. You just upload your design and choose the material and surface finish. You can even add threads. The system automatically finds the price, and if time is not a big constraint for you, you can get it for cheaper by selecting a longer build time. They offer a lot of shipping options and some of them are really cheap. Also, don't forget to check out the coupons they have.
You can try them out yourself with the link in the description. For this project, I ordered 2 cylinder heads to use as a second stage. I should receive them within a week, so meanwhile, I can finish everything else up. Let's get back to the stage thing. If the first stage and the second stage have the same size and the compression ratio, let's say they are both 1 liters and have a compression ratio of 10 to 1, then the first stage will intake 1 liter of air and compress it to 100 milliliters and give it to the second stage. But the second stage is also 1 liter. So air will decompress to 1 liters and then compress back to 100 milliliters. So what is the purpose of the second stage, you ask? In this case, it doesn't work. But if the second stage has a displacement of 100 milliliters and has a compression ratio of 5 to 1, then the first stage can compress 1 liter of air to 100 milliliters, increasing the pressure tenfold, then give it back to the second stage, and the second stage can compress it again to 20 milliliters, increasing the pressure 5 times again. So the total compression ratio will be 50 to 1. This is pretty much the ideal second stage, but in my case it won't work, because I use these acrylic tubes as cylinders, and they're only sold in 3 meter sections. This is my third project trying to finish the remainings, but I still have more than a meter left, and I don't want to buy a new thinner one. Another method is using two stages with same displacement but varying speeds. So the first stage will spin faster to pump more air into the second stage. But then a noisy kinda complex gear system is needed, and also you need to add a second crank. I don't want to deal with that. Another method is having two stages with the same bore, but the first stage has a longer travel. This way, the first stage can have a higher displacement. But the problem with this is, to do this, you need a kinda complex crank with two different radiuses. And in this project, the crank is prone to breaking. It will be our bottleneck. I don't want to increase the complexity of the crank. So the method I will use is increasing the number of cylinders. There will be 6 in total.
And we won't have any melting issues since the parts from GLC CNC are here. Last time I had to get parts from aluminum done was for robotics competition in high school. And back then I didn't know anything about designing. Holding something that I designed here in flesh, made out of metal, is an amazing feeling. Last time I felt something similar was 3D printing, something that I designed for the first time. And the parts look great, top-notch workmanship. The dimensions are correct, threads are good, the post-processing is also great, there are no metal filings or chips, it's cleaned well, not oily at all. And packed in a way that they won't scratch each other. Let's get back to the stage thing.
There will be 2 sets of 3, where 2 pistons pump air into one. A single piston was able to increase the pressure to 40 psi. So by using this method, we should be doubling that. And since we have 2 sets of this setup, the speed will also increase. And there's also another benefit to this. Since there will be 2 cylinders as second stages, they will have a higher torque requirement. And if we put them in opposite size, their kickbacks will basically cancel each other out. Having 4 first stage pistons is also good, because it will also smoothen out the curve. By having 6 pistons, it also means there's 6 curves, but the curves have a 60-degree phase difference between them. So when we add all these curves together, yes, we get a higher torque, but it's smoother. This configuration is called Radial, and back in the day, most of the airplane engines used these configurations, but they always had 5, 7 or 9 cylinders. It was always an odd number. Leave a comment why that is, and I will explain it in the end of the video. With a compressor like this, having 6 cylinders and even number is not a problem. For the plates, I used to use MDF and acrylic. But since the new design has 5 more cylinders, acrylic won't cut it anymore, so I upgraded it to 5mm polycarbonate. If you never used polycarbonate before, don't try to laser cut it like me, it was a nightmare, it was horrible. It doesn't really cut, it just burns and creates this like nightmarish toxic fumes. Just use a CNC router. Finally, I soldered wires for the motors. I used cheap no-brand ones without a datasheet, but I'm hoping they will be fine.
I kinda showed the design, but let's go over it again quickly. What I'm basically doing is adding 5 more of everything to the old design. In order for the 6 piston rods to fit into the crank, I made them slimmer this time. But still the crank had to get a little longer. And now the cylinder caps and the bottom caps that support the cylinders are different for each cylinder. Additionally, I added the flywheel gear thingy and room for 2 motors to the backside. I also added a couple of connecting pieces in between the plates to support them better. Here, it should work like this in theory. But in reality, this was the reason the video took this long to make. There are simply too many parts and it took a while to print and find and buy everything. And yeah, the part that I'm kinda dreading is here. Wish it was this easy to assemble it in real life. But don't worry, it will look easy to you. Enjoy the time lapse. Last night I finished the assembly besides the pneumatic fittings and the tubing, but I want to try it as is to see if it works, so I hooked up the batteries and let's see. Works. Not gonna lie, this project was hard for me to finish, and it took a lot of time, but it's worth it. It's just worth it. Watching it turn and actually seeing the rods and the pistons tickles my primal brain like nothing. Look at it go, it's just beautiful. While I'm fitting the pneumatics, I will do a compression and a vacuum test for each cylinder. And starting with the cylinder number 1 with the aluminum cap, the metal shows the difference. It's already maxing out the gauge even when it's turning slowly. But of course, it might just be because I'm attaching the gauge directly without a tank. We'll test it for real soon. For an easy test, let's try to pop this globe. As I mentioned before, I'm trying the 2-stage setup with 2 sets. Meaning you can imagine the right side and the left side of the compressor as separate units. The bottom 2 left cylinders intake air from the room and pump it to the top left cylinder. The top right 2 cylinders again intake air from the room and pump it to the bottom right cylinder. The cylinders with the metal caps work as the second stage, and the air they are pumping go to the outlet, which in this case is hooked up to a globe. The globe is not popping, it started leaking, but the compressor part is a success. Here is how it looks from the behind. Sadly, I didn't have enough nuts to fill all the slots. And since it's holidays in Turkey, I can't buy more. So the flywheel is not in its ideal form. Let's try pumping a ball next. With 5 to 10 psi needed, it's more of a challenge, but it should still be a breeze for this beast. I don't know why, but I find this relaxing to watch. If you also do, enjoy. It's now time to find out how high of a pressure we can get. The old compressor was able to get up to 40 psi. With the second stage, we should be able to double that. The only problem is, I don't remember how much pressure these soda bottles can handle. I did look it up before the first compressor video, but it's been a while. Yeah, we broke the record, it's over 40 psi. The bottle did handle this much before, but 80 psi might be too much. Before continuing, I looked it up and it should easily be able to handle 80 psi. Feeling more confident now, so let's get going. As the pressure increases, the motor slows down a bit. To keep the speed, I have to increase the voltage from time to time. Yeah, past 80 psi, so I finally reached the goal I had in the first video. This should be enough pressure to spin many air engine types. I'm planning to design a couple of them as well, so make sure you subscribe and ring that bell. For now, let's use the pressure to blow up the glow again. And for the final experiment, I've seen people online making mineral water using CO2 cartridges. With enough pressure and time, all the gases in there should be able to diffuse into the water, making it bubble like a soda when I open the bottle and release the pressure. Let's give it a try. I looked online for suggestions and found that they generally put it under 40 psi and let it rest for a couple of days. But I don't have that much. So hopefully around 1 hour with double the pressure should be enough. It maxed out the gauge, and I don't want to break it, so let's let it sit for a while and continue when the pressure drops a bit. As the air inside the tank diffuses into the water, the pressure should drop. Here I forgot to open the valve to the tank and pumped it full force directly into the gauge, making the gauge start to the second lap. Hopefully it didn't break. The pressure inside the bottle is also quite a bit above the limit of the gauge now.
So I filled the bottle with 100 psi of air. I'm guessing it's 100 psi, but I can't be sure. I will explain why. It maxes out the gauge. So this should basically put enough air in that when we open it like an hour from now, it should bubble like a soda basically. So the reason I don't know the exact pressure is we maxed out the gauge. I didn't think we could go further than this, so I bought a 80 psi 6-bar gauge and we maxed out. And it's holidays in Turkey right now, so I can't just go and buy a new one. So we won't know the exact limits of this machine, but I'm guessing it's around somewhere of like 120 psi, which is, I think it's incredible. I'm not 100% sure how much pressure we can reach right now, we did reach right now, but interpolating from the signs we have, it shows 80 and we go to the limit and it should be about 100, I'm guessing.
It's been about an hour, so let's see if it will burst like soda. The pressure dropped to 90 psi, so at least some air should be in the water. Okay, it didn't burst, but this fogging up also looks cool. The water is filled with tiny bubbles, so we didn't make it burst like a soda, but we accomplished something else. We visualized the worst nightmare of every diver: decompression sickness, where the divers spend time in depths with high pressure and come up to the surface fast with more than normal amount of gases diffused into their blood. Just like this, bubbles form in their veins, clogging them up. I'm really curious how this water tastes, but it should have quite a bit of machine oil in it, so I think I'll pass.
Thank you for watching the video. You can click the join button to join our 3 channel members. That's one of the best ways of supporting the channel, but not the best one. The best one is sharing the video. If you are someone like me who likes to design and create stuff, check out GLC CNC. They offer great services with great pricing. Before you go, I previously asked why Radial engines has odd number of cylinders and why it doesn't matter for our compressor. We can think of a compressor like this as a 2-stroke engine, so it only has compression and intake strokes. But the Radial airplane engines has a 4-stroke cycle, which means each cylinder produces power only once every 2 crank turns. So the order of power strokes of these cylinders, which is basically called firing order, needs to be in a way that the engine produces smooth and continuous power. If all of the cylinders fire one by one, then in the first rotation, the engine will produce a lot of power because each cylinder will fire bang, 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 back to back. But in the second rotation, then none of the cylinders will fire because they are not in the power stroke anymore. This is not desirable because the power output will be really jerky. So the engineers found another way of firing the cylinders which made smooth power. For a 5-cylinder radial engine where every other cylinder is firing, the firing order will be 1, 3, 5, 2, 4, and then repeat 1, 3, 5, 2, 4, 1, 3, 5, 2, 4. But with an even number of cylinders, this is not possible. Let's try with 6 cylinders. Firing every other piston, it will be 1, 3, 5, and then it should be 1 again. So it will just repeat 1, 3, 5, 1, 3, 5. The even numbered cylinders will never fire. Let's say if they did, then what would happen? 1, 3, 5, then we should power the 6. If we do that, we didn't skip, so the power output will be jerky. If we don't fire the 6 and then we have to skip to 2, then there's a bigger gap than normal. It's pseudo-random. Like, it's not random, but it's basically not smooth. And this is why all the radial engines, as far as I know, have odd numbered cylinders.